Hello, so this is lecture 9, and we will continue with our discussion on chapter 16, which is how the wave propagates along a medium. Okay, so what did we discuss so far? We discussed the fact that if I cause any disturbance for a medium, some waves would start propagating. We also did analysis in case of a traveling transverse wave, and we agreed that it will look like a sinusoidal function, okay? Y of x and t, it will be a function of the position x and the time t. It will be some amplitude multiplied by the sinusoidal function that has kx, omega t, and some angle phi associated with it. The last point we discussed was the speed of waves. Okay, here you have to remember that the speed of waves, v, it is lambda f, but it is independent of lambda and f. Okay, it's actually dependent only of the medium the wave is propagating in, and the v is square root for the tension divided by the mu, where the tension is a property of the string. Okay, and the mu is mass per unit length. Again, it's a property of the string. Today, we're going to discuss the last point in this chapter, which is rate of energy transfer. What I want you here to see, I'm sending here a wave, okay, I'm sending a pulse, and I'm observing what's happening to this mass m. Waves, when they go through any medium, when they propagate through a medium, they transport energy, okay? For example, if we observe what's happening over here, I sent a pulse. First, the mass was motionless. It was at equilibrium position. But once the wave reached it, it caused this mass to go upward. So there is a change in energy. The mass now has more gravitational potential energy because it was lifted. So there is an increase in its gravitational potential energy. Okay, so in this section, we're gonna discuss the rate at which energy is transported along a string. Okay, now imagine here that there is a string vibrator and there is a string attached to it from one end, and I am sending a wave along the string. Okay, the source of the energy is this mechanical vibrator or string vibrator attached to one end of the string. It makes the string move up and down. This way, energy enters the system and propagates along the length of the string. Each element of length dx, so let's consider this element here in red. So this element of length dx, it has mass dm or delta m, okay? And it oscillates vertically, right? It goes up and down. It goes up and down. It oscillates vertically in simple harmonic motion. As it's propagating, it has both kinetic energy, so it has both kinetic energy because it has speed, and gravitational potential energy because it's going up and down. So kinetic energy, we will refer to it by dk, and gravitational, so here by dk, I mean infinitesimal kinetic energy. That is very small amount, that is kinetic energy associated with this very small segment of the string, and it has gravitational potential energy. I would refer to it by du, okay? What is kinetic energy? Kinetic energy, if you remember, kinetic energy of an object having of an object of mass m and moving with a speed v is half mv squared. Since here I'm talking about a very small segment of the string, so it will be half, instead of m, it will be this very small mass, that is dm v squared. Okay, now what is v? Remember that y of x and t is equal to A sine kx minus omega t plus phi. Okay, so what is V? It is dy by dt. So Vy, which is dy by dt, it will be minus omega goes outside, so minus omega times A cosine of kx minus omega t plus phi. Okay, so this is my Vy. And what is dm? Okay, what is dm? Here you have to remember that mu is equal mass over length. Okay, so dm is mu times L, which is dx in this case, because it is this infinitesimal segment of the whole thing. So now I come to my equation. dk is half dm Vy square. Instead of dm, I'm gonna put mu dx. So dm is mu dx. And instead of Vy, I will put this thing, which is minus omega A cosine kx minus omega t. There is no reason here to put phi. It won't cause any difference, okay? So square. And this here, it will be half mu, and the dx, I put it at the end. So now what do I have? I have half mu omega square A square, because I'm making the squaring, cosine square kx minus omega t dx, okay? If I take a snapshot, okay, I don't have to look at all times. If I take a snapshot at time equal to 0, dk is equal half mu omega square A square cosine square kx dx. Now, if we integrate this dk over all the string, okay, so now I want to get the kinetic energy over all the string. So I'm gonna integrate over the whole string. If I integrate over the whole string, implies dx will be from 0 to lambda. Okay, so what will I get? Kinetic energy for 1 lambda is the integral of half mu omega square A square cosine square kx dx. This is equal half. I get the mu omega square A square outside because this is constant. And I will have inside 0 to lambda cosine square kx dx. Okay, what is the integral of cosine square kx? Here you have to remember the identity. Cosine square x is equal to half plus half cosine 2x. So I make the integration of half plus half cosine 2kx dx. The integral of half is half x. The integral of half cosine 2kx is 1 over 4k sine 2kx from 0 to lambda. Okay, and I have to get here, let me do it on the side. The integral of half x from 0 to lambda. So I have, let me put it here. So I have 1 over 2 x plus 1 over 4k sine 2kx from 0 to lambda, right? I cannot write it in a better way, so just imagine it like this. So it will be half lambda, right? So this will give me half lambda minus half times 0, right? Plus 1 over 4 sine this is sine 2kx. So it is half sine 2k times 2 times lambda. Sorry, okay, minus 1 over 4k. So here there is 1 over 4k sine of 0. Okay, now half lambda is half lambda, it stays. minus half times 0, that's 0. 1 over 4 k sine 2k lambda. Here you have to remember that k is 2 pi over lambda. So I will have 2 sine 4 pi, which is 0, minus 1 over 4 k times sine 0, which is also 0. So the integral of this whole thing, the integral of this whole, so this thing gives me only half lambda. Okay. It gives me half lambda. So the last answer will be 1 over 4 mu omega square a square lambda. So this is for the kinetic energy. Now for the potential energy, because the total energy carried by this segment over here, by this infinitesimal mass, is kinetic energy plus potential energy. So potential energy is du is equal half k y squared. Okay, but what is this k? This is not k, which is this k over here is string constant. Okay, so it's a property of the string. It is not the wave number. Okay, so to get this k, you have to remember this formula. Omega is square root k over m. Okay, so k is omega square times m. So I come here to du is half k y squared. So instead of du, I'm gonna put, instead of k, I will put it is dm times omega square times y square, which is half dm omega square, and y is nothing but a sine kx minus omega t square. So I get du equal half mu omega square a square sine square kx minus omega t dx, because here I use the fact that dm is mu dx. Okay, again at t equal to 0, I get this formula. I do the integration. I will be stuck with sine square kx. Sine square kx is half minus half cosine 2x, and if I do its integration, I will get u at a total u as a function, potential energy for one cycle is 1 over 4 mu omega square a square lambda. So the total energy E lambda, that is total energy in one wavelength of the wave, is kinetic energy plus potential energy, and this is half mu a square omega square lambda. Sometimes they call it energy the wave is carrying in one cycle. Okay, so they may ask me, find the total energy in one wavelength of the wave, or find the energy the wave is carrying in one cycle. Okay, now power, it is energy transfer over time. It is E lambda by time. It is half mu a square omega squared lambda over time, over the period, but lambda over the period is nothing but the speed, okay, speed of the wave. So the power is half mu a square omega square v. The unit for that is watt. Remember, the unit for energy is joules. Okay, here the unit is joules or J. The unit for power is watts. Okay, so they may ask me to get the power, or they may ask me to get the rate of energy transfer. So depending on that question. Let's start now by solving one exercise. So the wave function for a wave on a taut string is given by y equals 0.35 sine something t minus something x plus pi over 4. Here you have to remember that this is a, okay? Whatever is multiplied by t is omega. Whatever is multiplied by x is k. And this is the phase constant phi, okay? Now, where x and y are in meters, t is in seconds, so everything in SI unit. The linear mass density mu is 75 grams per meter. So mu is 0.075 kilogram per meter. Okay, all the formulas we're gonna use are over here. So to change from gram to kilogram, we divide by 1,000. Okay, so the first question, calculate the speed of the wave. So V is equal, you can say it is lambda, V is lambda F, and then you have to get lambda from K, and you have to get F from omega, but I can just use omega over K. So it is omega over K. Omega is 10 pi over K, which is 3 pi, and this is 3.33 meter per second. Okay, so calculate the average rate at which energy is transmitted. So we want power. Okay, so this is equal half mu times omega square times A square times V. And I will just plug in my values. So this is half mu, it's given 0.075 times omega, it's given 10 pi square times A, which is 0.35 square times V. I calculated it in parts A, and power is 15.1 watt. Okay, the last part, calculate the energy contained in each cycle of the wave. So the energy is P times the period, or I can use this formula. Okay, so this is equal half mu omega square. Actually, to make it easier, we can calculate the period. Period is omega. Period is 2 pi divided by omega. And this gives me 2 pi divided by 10 pi, which is 0.2 seconds. So energy is power, which is 15.1 times 0.2, and this gives me 3 joules. Okay. The other way is to say energy is equal half mu omega square A square lambda, and you get the lambda from 2 pi over K. You have the K, so you solve it and you get the same answer. Or you say it's power times periods, and it is half mu omega square A square V. V times period is, it's again lambda. Okay. All of them should lead you to the same answer. Let's solve another exercise from the booklet. So a sinusoidal wave is in a string is described by the wave function a 0.015. So this is a sine something x. So this is k minus 50t. So this is omega. Okay, so we have all of them. X and y are in meters. T is in seconds. The linear mass density of the string is mu is equal to 50 grams per meter. So mu is equal 0.05 kilogram per meter. Here, I just want to warn you that the solution in the booklet is wrong. So the solution over here is correct. So part A, find the maximum transverse acceleration of an element of this string. So the maximum AY, it's over here. It is A amplitude times omega square, and this is equal 0.015 times omega is 50 square, and this gives you 37.5 meter per second square. Okay, part B, separately. Determine the maximum transverse force on a 1 centimeter segment of the string. So I have L is equal 1 centimeter. You directly change it into meter by dividing by 100. So it is 0.01 meter. Okay. The force F is equal to what? The force F is equal to the mass times the acceleration. Okay. And if they're asking for the maximum force, so I have to take the maximum acceleration. Okay. But how much is M? So F max, I want it. M is an unknown. And AY maximum, I have it. I just calculated it. Okay. So I need to find M. Okay. To find M, I use the fact that mu is equal 0.05 kilogram per meter. Okay. But mu is equal to what? It's equal to mass divided by length. Okay. So implies, or let's put it down here, implies mass is equal mu times the length, implies M is equal, mu is 0.05 times my length is 0.01, implies M is equal 0.0005 kilogram. Okay, so I got the mass. Now F maximum transverse is equal to this M, which is 0.0005 multiplied by AY maximum, which is 37.5, and F maximum, the maximum transverse force is equal to 0.01875 newton. Okay. Part C. State how the force found in part B compares with the tension in the string. So here we want to calculate the tension. You have to remember the formula. V is square root of tension over mu. I square both sides, so V squared is equal to square root is equal to tension over mu. So tension is equal mu times V squared. Mu, I have it. I don't have a problem. So I want to find V. I use V is equal omega over K, which is equal, omega is 50 over K, which is 0.8. It gives me 62.5. You just use your calculator, meter per second. Okay, so now tension is equal to mu, which is 0.05 times 62.5 squared, and this gives tension equal 195.3 Newton. So how does this compare to F maximum, which is 0.01875? It is much bigger than F transverse. Okay. Finally, part D, let's do it here. How much energy is the wave carrying? So we want the energy the wave is carrying on one wavelength of the string. So I want the energy here. Okay, so this is the energy. It's half mu omega square times A square times lambda. Okay, let's write this somewhere else. Here. Okay, RD. E is equal to half times mu times omega square times A square times lambda. So is equal to half. Mu is 0.05 times omega, which is 50. So 50 square times A, which is 0.015 again square times lambda, which is 2 pi divided by k, which is 0.8. Okay, so here I use the fact that lambda is equal to 2 pi over k. Okay, so I just use the calculator and we get the energy the wave is carrying in one wavelength is equal to 0.11 joules. And by this, I reach the end of today's lecture. If you have any questions about it, just send me an email. And this is to remind you that you need to submit your assignment by tomorrow 8 p.m. Okay, so you still have today and tomorrow to work on your assignment. So that's it for today. Bye-bye.